Guys, let me know when to start.
Yeah. Very good evening to all of you. I am Shantan Mandal, and on behalf of the IISER Maths Club, I welcome you all to the second online club meet. And today's club talk is by Mr. Harsh Patil, who is a PhD student at our university in the Department of Maths. He is also our ex-club coordinator. So he'll be giving a talk on the Pigeonhole Principle. You may start now.
Thank you for the introduction. So let us start. Okay, so as you all know, I'll be talking about the pigeonhole principle. So the statement of the principle is very simple, but as we will see that it has many interesting consequences, and it is quite surprising that one could prove such things using such a simple tool. Okay, so let us look at the statement. Okay, so what does the principle say? If we have k plus 1 objects and we place them in k boxes, then at least one box will contain more than one object. Okay, so and one could easily justify this saying that if all of the boxes contained one or less than one object, then in total we can have at most k objects, right? So that's in short the proof of this statement, right? And sometimes we need a stronger form of this statement, which says that if we have k r plus 1 objects, okay, and we are putting them in r boxes, then at least one box has more than k objects. Okay, because let's say that each box had k objects, then we can have k or less than k, then we can have at most k times r objects. So that would contradict the fact that we started out with k r plus 1 objects. Okay, so these statements are pretty obvious, and let us now look at how they can be used to prove interesting things. So here goes the first application. This okay. So the theorem says that any real number x, uh, given any real number x and any natural number n, we there exists a rational number p by q such that x minus p by q is less than 1 upon nq. So what this means is that we are approximating this real number using this rational p by q, okay, and we are the error is 1 upon n times q. So what we would ideally want is that the error is as small as possible, and the denominator of this rational number should not be very large. That is the ideal situation. That's what we want. Okay, so let us first see why this is interesting. Okay, so let's say we can always get a rational number p by q such that the error is 1 upon 2 times q. Okay, so how do we do that? Look at this interval qx minus half, closed interval up to qx plus half. So this is an interval of length 1, and in any interval of length 1, there has to be at least one integer p, and that integer will satisfy this inequality, right? Because it lies in this interval. Qx minus p will be the mod value of qx minus p will be less than half, and now you divide this whole thing. Just a second. Yeah, so now you divide this whole thing Okay. By mod q and you get this. Okay, so now the challenge is to do better than this, better than 1 upon 2q. Okay, so by the way, pigeonhole principle is also called the Dirichlet box principle because Dirichlet was the first one to use this fact and to prove this very theorem. Okay, let's go. Right. So now, how do we prove this? Now, consider these numbers 0 times x, 2x, up to n times x, and consider their fractional parts. Okay. Now, all of these fractional parts lie between this interval, close 0, open 1. And now, what we do is divide this interval into these n equal parts. Okay, now since now here what are our boxes and what are the pigeons? So these fractional parts are the k plus 1 pigeons and these are our k boxes. So as our theorem, as our principle says, at least 2 of them must lie in the same interval. So and when so let's say these two r times s and s times x, these two lie in the same interval. That would mean that their difference is the mod value of their difference will be less than 1 by n, right? Because the length of all of these intervals is 1 by n. So now let us use the fact that a number is the sum of its fractional part fractional parts plus its integer part. So here a is equal to the integer part of r times x, and b is similarly b is the integer part of x times x. So just input these two things, and what you get is this. So now again, what we are almost done here. What we will do is divide the whole thing by mod of r minus s, and what we'll get is that x minus okay, b minus a divided by r minus s is less than 1 upon. Yeah, I'm sorry, I'm not used to writing with this device, but anyway.
Yeah, that's okay.
R minus s times n. Okay, so r minus mod of r minus s is our q that we wanted, right? So this is something interesting and maybe a little too technical for you. So this next result, this next application will be somewhat interesting, more interesting than this one, I feel. So okay, so this is called the theorem on friends and strangers. So let's say in a party you have 6 people, and if you pick any pair of them, then they either know each other or they don't know each other. They're either friends or they're strangers to each other. Okay, so we are not allowing the possibility that person A knows person B, but B doesn't know A. Okay, so in such a scenario, we have that there will be a set of a subset of 3 people out of 6, such that they either all know each other or they all don't know each other. So how do we model this situation? So we model this using something called as a graph. So a graph consists of vertices and edges. So we will represent those 6 people by vertices with these dots and edges. So the edges are lines that connect these 2 dots. So if 2 people are friends, we will label this edge as blue, and if 2 people are strangers, then we will label this edge as, we'll color this edge as red. Okay. So there are various possibilities. Like in the first possibility, that all of them don't know each other, or then, so all of these possibilities are covered in this picture, and you can see that in each of them there is a subset of 3 3 black dots. Okay. And these are the dots that are promised to you by this theorem. So they either form a blue triangle or a red triangle. So blue triangle corresponds to 3 people that all know each other, or and red triangle is a subset of people that don't know each other. Okay. So a little homework for you. Just calculate how many such possibilities are there. It's how many such colorings
2 raised to the power 6
are there. Right. So yeah, you're right. So no, not 2 raised to the power 6. First, tell me how many edges are there.
like 6 edges would be there, right?
No, 6 people are there, but edges are how many? So edges would be
62,
62, right? And for so how much is this? 6 factorial, 2 factorial, 4 factorial. That would be 6 into 5 divided by 2. 15. Right. And for every edge, you can either color it blue or red. So 2 to the power 15 possibilities are there. Right. So yeah.
Okay.
So, but we don't need to, given this theorem, we don't need to check for all of them. Yeah. Right. So, how do we prove this using the Pigeonhole principle? Okay. Now, let us fix an edge. Okay. Let us say we are talking about 1. Okay. Now, it is connected to 5 different people. Okay, and so what will happen that one of these edges, so let us for now assume that they are all blue, all of these edges are blue, and it can happen that one of these, so these will have 3 edges between them. Okay, so it can happen that one of these 3 edges is blue. In that case, we will get, so let us say that one of these, let's say 2 and 3. Let us say the edge between 2 and 3 is blue. What this will give us that 1, 2 and 3 form a blue triangle. Okay. The other possibility is that none of these 3 edges are blue. In that case, they are all red, and in that case, 2, 3, and 4 will form a red triangle. Okay, so in either case, what we are getting is that we are getting a monochromatic triangle, a triangle of the same color. So yeah, we are done with this proof. So this proof doesn't seem like much, okay, but so this is actually a, a special case of a theorem called Ramsey's theorem, which says that so let's say we are given two positive integers r. Okay, not able to write. So we are given two positive integers r and s. Then there is some large integer k, such that for every possible red-blue coloring of the complete graph on k vertices. So what do I mean by a complete graph? I will take k vertices and connect all possible edges that are there. So a complete graph on these, how many are there? 6 vertices. So what we had here was the complete graph on 6 vertices. You can have complete graph on any number of vertices. Okay, so if I take this complete graph and and I color the edges in by red or blue, then any possible such coloring will either have a complete subgraph of r vertices or a complete subgraph of r vertices which is red, or a complete subgraph of s vertices which is entirely blue. Okay, so what we had was the special case r is equal to s is equal to 3 here. Okay, so and the complete graph on 3 vertices is nothing but a triangle. Okay, so notice that if we took, instead of 6, we took 5 here, let's say, then it wouldn't work. Why? Because it's okay. Let me use blue and green, blue and red. Blue, stop. Yeah. So yeah. Okay. So and okay, I missed something. So what I wanted to do here was, yeah, as you can see, this is the graph that I wanted to draw here, right? So, right. So as you can see that this graph on 5 vertices, this complete graph, and I've colored it as just red and blue, and this has neither a blue triangle nor a red triangle. Okay, so so it doesn't work for 5, it works for 6, and for any number greater than 6, of course it will work, because we can just choose a subset of 6 vertices, and since it holds for 6, then we'll have either a red triangle or a blue triangle. Okay, so for the smallest integer that this theorem holds, we call it the Ramsey number. Okay, let me go back to red, black. So we call it the Ramsey number of or comma S. Okay, so the theorem states that there is a large enough integer capital K such that we have either a red complete subgraph or a blue complete subgraph. So because so what the earlier theorem told us was that R 3,3 is 6. And this is still like, so people have figured out the Ramsey number for various possible values of R and S, but only for some small numbers, some vertices, some subset of vertices among these, and we have considered we are taking all the edges among those vertices. Okay, so in this graph, if I take these three vertices and just take all the edges between them, this is a subgraph of this graph. Okay, right. So yeah, so I was telling you about Ramsey numbers. So these are the yellow ones that are still not known to us. What exactly we know that they lie between 4,6 lies between 36 to 41, but we don't know the exact number. Right. Okay. So and I'm not going into the proof of Ramsey's theorem, but it's quite easy to understand, and I hope that you go back and look at some nice book on combinatorics, and you'll find the proof there. It's using induction. Okay, so now now we are going to the last application of Fermat's theorem. The last application, which is the Fermat's theorem. So this one is from number theory, and so what this says is that every prime number which is congruent to 1 modulo 4 can be expressed as a sum of 2 squares. By the way, if someone has a question, you're typing it in the chat box and I'm not really paying attention. So why don't you just turn on your mic and ask? Yeah, so far if you have a question, just turn on your mic and ask.
Excuse me, sir.
You can call me Harsh.
Yeah. Bhaiya, in the previous one, when you say complete subgraph, this means that it should be closed.
What do you mean by closed?
Closed means closed figure.
No. It's not about the figure as such. Okay, so what I mean by a complete subgraph is that okay, where was that? Yeah. So what do I mean by a subgraph is that we are taking the thing is that a graph is just a bunch of vertices and how they are connected to each other. It doesn't matter how they are drawn. So this graph and okay. This graph and this graph are the same. What we really care about is that which vertices are connected to which vertices. Okay, so for example, this is a graph on four uh, four vertices, but it is not the same as this graph. Okay, so it doesn't matter how they are drawn or they are like a closed figure or anything. We just care about which vertices are connected to which ones. Okay, so any more questions, or did you? Is it clear
Yes, sir,
now?
very good.
Okay, so now last question is now the last application is for mass time, which says that every prime number p, which is one congruent to one modulo 4, can be expressed as a sum of two squares. So I don't know if you guys are familiar with modular arithmetic, but what I mean by one modulo 4 is that 4 divides p minus 1. So what are the primes that are congruent to 1 modulo 4? 5. Then yeah, 9 is not a prime. So okay, let's just go one by one. 6 is not a prime. 7 is congruent to 3 modulo 4. 8, 9, 10. 15. Yeah, 13 is another one. Then can you guys tell me whether 17 is, so yeah, 17 is also 1 modulo 4. Okay, so primes can either be congruent to 1 modulo 4. They cannot be congruent to 0 modulo 4, because that would mean that 4 divides that number and then it cannot be a prime. So if it is congruent to 2 modulo 4, then it will be of the form 4k plus 2, which would mean that 2 would come out. So then again, it cannot be a prime. So a prime is either congruent to 1 modulo 4 or 3 modulo 4. Okay. So we are saying that every prime which is congruent to 1 modulo 4 can be expressed as a sum of two squares. That means that there exist x and y, sum x and y is that x square plus y square is equal to p. Okay. Now, why do we care about primes? And so the answer is on the next slide. Okay, so this is called a Diophantus identity. Dio. And what it gives us that if we have two numbers which are both sums of two squares, then their product is also a sum of two squares. So you can verify this identity by just using high school math. Okay, there are more questions in the chat, but let us get to them in the end. Yeah. So yeah, so we can yeah. So we know that any natural number is a product of primes, can be expressed as a product of primes. So if for each prime number we have this, we can express it as a sum of two squares, then we know that the number itself can be expressed as a sum of two squares. Okay, so how do we prove this? So this proof is a little bit long, and yeah, so we'll be using some theorems that were already known. So for now, take them for granted. Okay, so first thing that we are going to use is Wilson's theorem, which says that if P is a prime, then P minus 1 factorial is congruent to minus 1 modulo P. So just to remind you, whenever I say that A is congruent to B modulo N, I mean that N divides P minus A. Okay. So yeah, so if p is a prime, then p minus 1 factorial is congruent to minus 1 modulo p. Actually, this is a if and only if statement that if this condition holds for some n minus 1 factorial is congruent to minus 1 modulo n, then n is a prime. And for small values of n, this can actually be used to check whether a number is prime or not. Okay, but for large values of n, this calculating this n minus 1 factorial becomes computationally expensive. And then actually it's a very nice problem in computer science. How do you check whether a number is prime or not in an efficient way? But yeah, that can actually become a separate talk. So okay, now using this fact, using Wilson's theorem, we will prove that for any prime p, there is an integer x such that x square is congruent to minus 1 modulo p. Okay, so let us do that. So we take x is equal to 2k factorial. Okay, now let us square it. And in the second step, what we have done is we have replaced 1 with minus 1, and we have multiplied minus 1 at the end. And we have done this for all the things in the second. In the second product, and so that gives us a minus 1 to the power 2k at the end. Okay, and so for people that are not familiar with modular arithmetic, okay, so whatever happens in usual addition and multiplication, it also happens in modular arithmetic. So you can add modulo and you can also multiply. You can only divide when p is prime, but yeah, we don't really use that all that here. Okay, so and so what do we get here? So we can replace minus 1 by p minus 1. Why? Because p minus 1 is congruent to minus 1 modulo p. Why? Because p divides p minus 1 minus minus 1, which is p. Okay, so simple thing. Or you can say that p is congruent to 0 modulo p, and minus 1 is congruent to minus 1 modulo p. We can just add these two things and get this. So similarly for minus 2 up to minus 2 times minus 2k. So what is k? So we started out with p is equal to 4k plus 1, and we got that k from here. So p minus 2k is 2k plus 1. So this value is 2k plus 1. This will be smaller than that up to p minus 1. So what we are getting here is p minus 1 factorial. If you think about it, here's 2k. This is 2k plus 1 all the way up to p minus 1. So this is p minus 1 factorial. And if you remember the previous theorem, this is congruent to minus 1 modulo p. Am I running out of time? Right? So we started at 6:30, right? So I'm fine, I guess. Yeah. Am I audible?
Yes.
Okay, great. So now how do we use this x to get what we want? Okay, so we we will find a pair of integers u comma v such that mod u and okay. Mod u is greater than root p, mod v is less than root p, and u square plus v square is congruent to 0 modulo p. Okay, so I'm saying all of these things without really justifying them. So how will this help us? So so what we're going to do is that show that there exists a pair of integers u and v such that their mod value is less than root p, and their u square plus v square is congruent to 0 mod root p. So what would that mean is that this integer u square plus v square lies between 0 and 2p, right? And okay, u v not equal to 0 comma 0. Okay, so that is how we are that is how we are avoiding 0 here. And so yeah, so the only integer that lies between 0 and 2p that is congruent to 0 modulo p is p. Do you guys agree with that or not?
Yes.
Yes.
Okay. So this will force u square plus v square to be p. Okay. So now okay, so now if we have now how we will show that is that we will show that this u plus x times v is congruent to 0 modulo p. So how does this imply this? So okay, let us square this thing. U plus xv whole square. This is nothing but u square plus x times v square plus sorry, that is not. Right. So I seem to have missed something. So the idea was to factor this equation like this, and so what this would be is u square minus, so x square is minus 1 and v square, which is u square plus v square. Okay, so what we want is that right. So oh yeah, sorry, yeah. So let's say we have u plus x times v is congruent to 0, then plus. Okay, yeah. Let us skip this part for now, and yeah, I seem to have missed something here. I will share this with you guys later. Okay, so let me move to the last part of my talk. Okay, so I have some homework for you guys where you have to apply this pigeonhole principle for to prove these things, and these are very nice applications of pigeonhole principle where you can get a feel for how to apply it. So the first question is, how do you so you are given a square of side length 2, and if you are given 5 points inside this square, then you have to show that there are at least 2 points that are at distance root 2. Okay, so so the hint for this problem is also given below, that you have to divide the square appropriately into smaller parts, and so that you can prove this. So then there is another exercise for you. So when we divide rational numbers, when we obtain the decimal expansion of a rational number, what we do is we divide this b by a and play with the integers, the long division that we used to do in high school. Okay, so and in that we used to get, so for example 1 by 3 is equal to 0.333 and so on. So we have that whenever we are doing this, so this always repeats after some time. So for instance, for some other rational number you could get 0.539, 539 and so on. Okay, so but how do we know that, how do we prove that for any given rational number a by b, this decimal expansion will always repeat after some time? And
We can show this by saying that after after dividing by 10 times, and we get 10 remainders, then it must means it must
Right. Yeah, you are
repeat
thinking along
for
the right
smaller.
lines.
Yeah, for smaller values, if the denominator is larger, then we have to take larger values of n, and so we can say that after certain point the remainder will we have to get another remainder, and then we will show that it will repeat.
Nice, right. So you are already thinking along the right lines. I don't know who exactly was talking, but so who was it? Can you tell me your name?
Sorry, Prakash.
Right. So Shaurya Prakash was already is already thinking along the right lines about how to solve this. So the place where you apply the pigeonhole principle is that when you are dividing by some number, then the remainders. Say, let's say you're dividing by some number n, then the remainders can only be 0, 1, all the way up to n minus 1. So there are only n possibilities for the remainders, and so when you're repeatedly dividing, then the remainder must repeat after some time. So I'm not going into much detail, but I want all of you guys to try this. And so this is actually a uh, third homework problem for all of you. Third exercise. So given any 5 points on a sphere, there is a hemisphere that contains 4 of them. Okay, so so by hemisphere here I mean that it doesn't have to be the northern hemisphere or the southern, or it can be anything. It can be, so let's say we have this sphere, so it can be a hemisphere which is sort of like this, tilted. Okay, but there will always be some hemisphere that contains 5 of these points. Sorry, four out of these 5 points. Okay, so yeah, so that's it. I'm sorry about this last part. I seem to have missed something, but yeah, I will share the reference for this part, and you can read it from there. So that's it. There are many more applications of pigeonhole principle. I wasn't sure how much time I had, so I did not include other things. But yeah,
Bhaiya, in first problem, the square are divided in 4 unit length square. Then there are 4 choice and 5 points. Then 2 of them will be in one square. Then in a square,
so you are saying I should go like this,
yeah,
and so let's say you have
4
5
choices.
points. So 2 of them will be in the same, yeah,
Same square, and
right.
maximum length in the square is √2 because the length is 1. Maximum length because
Yeah.
if
So
it
the
placed
side
in
length
corners,
is 1,
opposite side corners.
and maximum distance is this diagonal that you can get, and that is of length √2. Yeah, you're right. That is more or less the solution of this problem.
And I have a problem.
Oh, you have?
Yeah,
Tell
I
me.
have a problem. Means in a plane there are endpoints, and they are
Okay.
joined by 3 different colors. Then there will be a monochromatic rectangle. So, proof that there will be a monochromatic rectangle only using Pigeonhole principle, not on graph theory.
Right.
What will be the
So,
answer?
yeah, that is a nice problem. Coordinators, please tell me how much time we have. Like, are we supposed to? Because we can discuss this problem if we have time.
Yeah, you can discuss it like since it's the doubt session already, so you can discuss it.
Great. Okay. So, yeah. So let us look for some blank space. Okay, so this is our plane, and can you tell me this problem? So you have n points somewhere in this plane. You have this x-y axis. Okay. So can you please repeat your problem again?
N points, and we are joining them with 3 different colors.
So some randomly placed points, and we are joining them with. What do you mean by 3 different colors? We are coloring the points.
And like Ramsey theorem, but we found a rectangle instead of a triangle with same color.
Okay, so there is no restriction on n, the number of points.
No restriction, only proof by Pigeonhole Principle.
So you have, so it has to be at least 4, right? The number of points.
Yeah.
And how many colors did you say?
3 colors. 3 colors.
Okay, 3 colors. So let me. Okay. I hope that other people are thinking about this and trying it. So we are coloring all.
Can you tell the problem again?
Right. So what I think the problem is
I
that
put this in chat box.
Right. There are n points. Then there are we connecting all of them or only some of them?
We connect all of them.
Right. So we are connecting all of them, and when we are given 3 colors and okay. So let me use the 3rd color. Oh, by the way, this is exactly the Ramsey. This is a sort of a generalization of Ramsey's theorem, which says that if you are given, let's say, n colors, then okay, let's say you are given 3 colors, and then you are given 3 integers r, s, and t. Okay, then you can find a large enough integer k such that if you take these points and color their edges in using these 3 colors, then at least you can find a complete graph of size r or of the same color or s or t. Okay, so what this problem is really asking us is to compute r 3, 3. We're given 3 colors and we have to find a triangle of the same color, right?
No, rectangle. Triangle, that means R3, 3, 3 is equal to 17.
So yeah, I was wrong. This is not really a generalization of.
We have not to find the number n. We only prove that there will exist a rectangle.
Okay. So let us start from one vertex and let us look at. So let's just say what happens for just one.
Yeah, we have to show this that it is true for every n.
Right. So if it is true for n is equal to 4, then it will be true for more than for greater than 4, right? Because then we can take a subset, and so yeah, n is equal to 4 is really the case that we are trying to solve. Okay, so we have this, right, and we have to show that. So what are all the rectangles that we can get here? I don't think it is true for n is equal to 4, because see, for n is equal to 4, this is the only rectangle that is there. Okay, and and we can use that, use the given 3 colors in such a way that this rectangle is not of the same color. So I think you have not read the question properly. Something is missing, right? Maybe there is some restriction on n that you missed. Okay, so I think these guys, coordinators, are making a website, and so you can we can have a sort of a section where we find interesting problems, so that they can post it there, and people can also post solutions, I think. So yeah, we can do that.
Yeah, we'll be making a website like that soon and launching it.
Great. Okay.
Okay, yeah.
Yeah, so nice. So that's it from my side. I'll stop presenting.
That was really an interesting session, and thank you a lot for giving your valuable time for this session. And I, on behalf of the Maths Club, thank you for this. So, and also thank you to the participants. I hope that you stay connected with us like this for further talks. Thank you.
So I would just like to add that it would have been it would have been much better if we were in a classroom and I was in like we had a blackboard in front of us, but yeah, this is how it is now. We have no option, but yeah, I hope I could.
Yeah, due to the COVID.
So will it be? Is there some? Will it be happening offline in some near future, or is that a possibility?
Yeah, actually, the main reason why we are conducting it like online is due to the first years are not here, and mostly some of the second years are also not here. So that was the main reason. But like maybe next month we'll be making it offline if everyone just comes back.
Okay, great.
Yeah.
Yeah, can you share the slide again? Because I want to screenshot to take. I want to take in screenshot of that homework.
Oh, okay. Yeah. So I think we can post this. You can take a screenshot, of course, but I think we can post this slides once the website
Yeah,
is
we'll be sharing it with you all, the slides.
okay. Great. So yeah, let us stop here. Good evening to. I mean, good day to all of you. Okay. Sure. Bye. I'll sign up.
Yeah. Thank you, sir.
Thank you, Bia.
Thank you, Priya.